It consists of 7 different topics. The first one is C bar A codes, C bar A codes, course slash acquisition codes, P type codes or the precision codes, Y type code derived from P codes or the precision codes, followed by L1 and L2 frequencies, L1 subband frequency of your GPS system, L2 subband frequency of your GPS system. After the L1, L2 bands, we'll be seeing about code pseudoranges, then satellite signal structure, the message system used in navigation, and signal processing techniques and its different types. To start with the C bar A codes, which we call it as course acquisition code, this consists of binary digits, which is operating with a chip rate of 1.023 megabits per second. This code stream will have approximately 1023 binary digits. So these binary digits are represented in zeros and ones. So that will repeat for every 1 millisecond. So totally we have 1023 zeros and ones together. So the duration of every bit would be approximately 1 meter per second. Sorry, not 1 milliseconds for every milliseconds, or it will be equivalent to 300 meters. So the satellite which is present with this type of C bar A codes enables the GPS receivers to identify what type of satellite is being transmitting with that particular code. And the C bar A code range measurement is always relatively less precise when compared to that of the precision code type. But however, this C bar A code is less complex in designing and is available to all the users. Most probably all the military users and the civilian users can use this C bar A codes. On to the next is that P code or precision codes. So these precision codes are a very long sequence of binary digits that will repeat itself. So the codes will repeat itself after 266 days. So the code type which is used at the first day and at the 267th day will be same. This means that this will make the P code type or the P code system having 10 times faster than C bar A codes. This codes will give us a data rate of approximately 10 times faster than your C bar A codes, which is if our code rate of your C bar A is 1.23, which I'll show you in the previous 1.023 megabits per second. So multiply that into 10. So you will be getting the precision codes data rate as 10.23 megabits per second. So since this P code will repeat itself after 266 days, this will have higher data rate. And in order to find the chip rates, we'll be dividing this 266 days long code into 38 segments, which is 1 week long. Okay. There will be 32 segments assigned to various GPS satellites. Yeah, there will be 32 segments assigned to various GPS satellites. Where each satellite will transmit a unique 1 week segment of P code, which could be initialized every crossing of Saturday to Sunday midnight. So when there is a transition of Saturday to Sunday, during that period the code will change. So the remaining 6 segments of the 38 will be reserved for the other users. So totally 38. Out of that, 32 segments are assigned for various GPS satellites, and each satellite will transmit a unique 1 week segment of P code that is initialized for every Saturday or Sunday midnight crossing. At that time, they'll initialize it. So the GPS satellites are usually identified by this 1 week segment of the P code. Using that, they will be identifying. So for example, a GPS satellite with ID PRN20. PRN is a pseudo range 20 refers to a GPS satellite that is assigned with the 20th week segment of PRN P code. If you have PRN 20, it resembles that it is being assigned for the 20th week of segment. If it is 18th, it is 18th week. So and it goes on. Okay. And the main purpose of going for this P code was your military purposes. The design was done for military purposes. Whereas the C bar A code was available for both civilian as well as military purposes. So let us go to the next code. Next type of code is your Y code. This Y code was derived from P code, where we'll be adding an weighted code. Okay, so we will be adding some encryption algorithms to the existing P code, and we will be deriving an unknown code, which we call it as W code. Okay, the adding of a W code. So the resulting of this P code with the W code would be giving us an encrypted code called Y code. So this Y code will be having a same chip rate, same chipping rate as that of the P code. And the encryption that is being used here is AES, which is anti-spoofing. Anti-spoofing encryption algorithm is used. So these were the 3 different types of codes. We had already seen the anti-spoofing technology in unit number 1. Anti-spoofing technique, which is used to encrypt your codes. So these CA bar A codes, P codes, and Y codes are the different coding structures which are being used in different users depending upon its need. If you use A civilian will be using C bar A code. If you are specifically using military purposes, will be using P codes. And if you want to encrypt in high-end security applications, will be using Y codes. So now let us see the L1 and L2 frequencies. L1 and L2 frequencies of this GPS satellite structure. Where do we use this L1 and where do we use this L2? So GPS navigation message is always a data stream that are being added to the L1 and L2 carriers as a binary biphase modulation with as low as data rate of 50 kilobits per second. So always the modulation scheme is used is your binary biphase modulation. So this L1 and L2 carriers will have 25 frames consisting of 1500 bits each, or each frame will have 1500 bits, or in total we'll be having 37,500 bits. And the transmission that will be taking place, the transmission of all these 25 frames will take approximately 750 seconds or 12.5 minutes. So the transmission of the complete navigation message will take 750 seconds or 12.5 minutes. This navigation message will contain the information such like the function of the time of the satellite, the satellite health status, the satellite clock correction, the satellite almanac, and the atmospheric data of the satellite. Okay. And this each satellite that it transmits own navigation message with information on the other satellites also can be done, such as determining the approximate location and health status of neighboring satellites, its own satellite, and so on. So that also can be monitored. The health status represents the power available, lifetime duration of that particular satellite, how much amount of solar power is left out, how much amount of fuel is present in the satellite, and all the informations like that. So that represents the health status of each satellite. Next is the code pseudoranges. The code pseudoranges and the phase pseudoranges are affected by both systematic errors or the biasing, and due to random noise also. So this random noise and systematic errors which is being obtained by the pseudoranges affects the GPS range determination. So for this we'll be using Doppler measurements which have been classified into 3 groups: satellite related errors, propagation medium errors, and receiver related errors. So all these 3 errors has to be determined and it should be eliminated. So for this, an appropriate Doppler measurement is needed. So there are systemic effects that are eliminated by appropriate combinations of observations of the satellite with respect to its point. Then the differencing between receivers, which could eliminate the satellite specific biases, and the difference between satellites that eliminates receiver specific biases. Next one is your double differencing pseudoranges, which has high degree free from systematic errors that originate from the satellites and from the receivers. And in terms of refraction, we'll be measuring the short baselines that are being put up at both the endpoints in order to eliminate the ionospheric refraction by combining the dual frequency data. So this is how we eliminate the error due to refraction. Then we have another difference, which is your phase pseudo-range difference, which we call in terms of antenna phase center variations. So this antenna phase center variations are being treated by multiple reflections. So by using this multiple reflections, we can approximate the point of observation for that corresponding satellite. Hey, the multipath is caused by multiple reflections of the signal that occurs at the satellite during signal emission. This interference between the direct and the reflected signal is always a noise that is generated randomly in nature. A similar effect called imaging is observed a similar effect imaging is being observed when a reflecting obstacle generates an image of the real antenna that makes distortion in the antenna pattern. So both the effects of multipath and imaging are considerably used in reducing the selection of appropriate antenna design when there is a reflection from buildings, vehicles, trees, large scale buildings, and so on. So by designing an appropriate antenna design, we can eliminate all the multipath effects and the imaging effects which occurs due to these reflections. And it is to be noted that the multipath is always a frequency dependent. Hence, carrier phases are always less affected than the code ranges. Therefore, the random noise that mainly contains the actual observation noise and the random constituents of the multipath are estimated by the satellite biases under the wave propagation system, which can be determined by the user equivalent range error. So this user equivalent range error is transmitted via the navigation message. So all the informations of this range error is also sent through navigation message. So here there are two tables. One is the source and another one is the effect which it causes. When you see a satellite, it is a source for clock bias and it also leads to orbital errors. And when we see the signal propagation, as the signal travels from one place to another place due to refraction of ionospheric, tropospheric of the nature of Earth's space, we get ionospheric refraction and tropospheric refraction. And at your receiver, due to the inefficiency of the antenna's design, we will be getting antenna phase center variation, the clock bias due to the satellite signal, and multipath reflection. So these all constitutes your code pseudoranges, range biases. Due to satellite, due to signal propagation, and due to receiver. Next is that how much amount of noise range does each and every code can generate, or how it is being tolerable. So the coarse bar acquisition code can have a noise of up to 10 to 300 centimeter noise, whereas precision, which is used in military, can have up to 10 to 30 centimeter noise, whereas the phase range is of 0.2 to 5 millimeter. Next topic is your satellite signal structure. The satellite signal structure is divided into three parts. One is the physical fundamentals required for designing a satellite signal. Second one, the components of the signal. Third is the pseudo random noise codes, PRN codes, how it is being used. So let us start with the physical fundamentals. So in the physical fundamentals, always we'll be using an electromagnetic wave to transmit our signals. All the data transmission occurs through propagation of electromagnetic waves that satisfies the Maxwell's equation. You would have studied Maxwell's 4 equations, equation number 1, 2, 3, and 4. All the electromagnetic waves will satisfy Maxwell's equation, whereas the satellite signal also uses electromagnetic waves, so it also satisfies the Maxwell's equation. So during the propagation of the wave, the field strength decreases with increasing in distance from the transmitting source, which is known to everyone. As distance increases, attenuation also tends to increase. So the measurement of that is given in terms of attenuation, measured in decibels. So we take a signal strength of about 1/2 of its original strength. So then we can calculate F is equal to 2 pi 1 divided by P, which is equal to C by lambda. So where F is the circular frequency of the measurement of satellite, lambda is the wavelength, P is the time period taken, and C is the velocity of light. So with this physical fundamentals, we will be deriving signal structure. how to determine the signal structure using your Doppler spreads. We have a symbol notation called phi, which is used to measure the phase of the signal. So this phase of the signal can be found out by the derivation of the phase with respect to time, which is f is equal to d phi by dt. So integrating the frequency between the epochs t naught and t, the phase will become phi is equal to limits t naught to t f into dt. So we assume a constant frequency which is set up to the initial phase to 0, and taking into account the time span at which the signal needs to propagate through the distance from the emitter to the receiver, then the phase equation can be obtained as phase phi is equal to f of t minus t tau. And from this you can find phase phi is equal to f of t minus tau by c, which is a relation. So in the case if a emitter is moving, that means your source. If a source is moving or a receiver is moving, the received frequency will be always Doppler shifted. So this shifting of the source or shifting of the receiver plays a major role in determining the relativistic effects. So we need to find this relativistic effects, which is proportional to the radial velocity or the range rate of the source with respect to the receiver. So we can find it as del f Doppler shifted is equal to fr minus fe. Fr is your frequency of the receiver, fe is the frequency of your emitter, which is equal to minus 1 by c v fe. After the physical components determination, we are going to see the components of the signal. What are the different components available in a signal is. So the different components in your signal of the satellite consists of oscillators that will generate a fundamental frequency of f naught. For example, if you take block 2 satellites, it is being generated over 1 day in the range of 10 power minus 13. After the oscillators will be having two carrier signals in the L band, which is L1 and L2. And if you want, we can additionally add some other L bands also, where in block 2A satellites they used L3 frequency also in addition to L1 and L2, such that the L3 carrier is always reserved for military users. And in block 2F satellites, they had given an option for L5 band, which was used only for civilian usage. The civilians want to use this L band was being implemented in that. So probably we had only in general L1 and L2 bands that are being modulated by some codes, either P or CA or W or Y, and they provided satellite clock readings to the receiver, and they transmitted the information such as the orbital parameters. So we have seen 6 orbital parameters all those information was being shared to the receivers. Then these codes always consist of a sequence of states with +1 or -1, where they correspond to binary 0 or binary 1 respectively. So this type of modulation which was used is called as biphase modulation, that was performed by 180-degree shift in carrier. The 180-degree phase shift in carrier with +1 or -1 indicated binary values of zeros or ones in biphase modulation. So if you take a nominal fundamental frequency f0 having about 0.005 hertz, then the determination of the carrier frequencies can be done by using this standard. So you can see that there is a table where we are fixing the fundamental frequency f0 if the usage is at 10.23 megahertz. That is a fundamental frequency. Carrier frequency L1 will be 154 times f0 and L2 will be always 120 times f0. This is standard relation in biphase modulation. So where this L1 will give you approximately 19.0 centimeter accuracies, 24.4 centimeter accuracies, and for this the precision code frequency will be 10.23. C bar A course acquisition code will be f0 by 10 because the P code is 10 times faster. So if I want to C bar A code, it should be divided by 10. So we will be getting 1.023. The W code, which is an encrypted code, is always 20 times divided by 20. So f0 by 20 we get 0.5115. And the navigation message frequency will be always f0 divided by 204600, which is 50 into 10 power minus 6 frequencies. So these are the frequencies used for different signals. In whichever signal you want to transmit, you can need to use this frequency. Next is the diagram representation. Diagrammatic representation of the biphase modulation scheme that you all are familiar. We have a carrier signal of sinusoidal in nature. We take a code +1, -1 to be transmitted. You can see that with respect to your code +1, our wave remains as it is. When there is a positive half, you can see from the diagram, compare this. When there is one cycle of carrier wave, the modulated carrier will also be the same in the case of +1. And in the case of -1, it will be inversion of that. So it will go from bottom to the top. You can see that inversion. This is your biphase. And again, it is being sent for this entire carrier +1, so +1. And the next is also positive, negative, so it also positive, negative. Again, we get -1, so it starts from here. This all diagrammatic representation, all are familiar with your digital communication also, I think so. Biphase modulation. Okay. So the course or acquisition code will have the frequency of f0 by 10 repeated for every 1 milliseconds. The precision code or the protected code or the P code will be repeated for every 266 days approximately. And the W code as we had seen earlier, is an encrypted version of P code which determines Y code. Sorry, it is not V code here. There should be Y. This is Y, not V. Y code. And the frequency of navigation message is 50 hertz at transmission of 30 seconds. When we want to transmit 1500 bits message. Both the L1 and L2 carriers are modulated by P codes, most precisely by Y also nowadays. The C bar A code is placed on L1 carrier in phase quadrature, that is 90-degree offset with P code. So this is how to place your C bar A code. On all these are being placed in the same satellite. The same P code, CA code, L1, L2, your Y code, W code, all are being placed in the same satellite. So the differentiation is that at some axes or at some angles or at different frequencies will be placing it. Okay. So the modulated carriers will be represented by this equation. L1 band, L1 frequency is obtained by the coefficients of A1, precision code of PT, WT, DT, cos F1T plus A1 C bar A is your cos bar acquisition code of A of T, B of T sin F1 of T. Whereas the modulated carrier of L2 is represented by A2 P of T, W of T, D of T cos F2 of T. In the frequency domain, the broadcast signal is characterized by split spectrum, and we are familiar that the split spectrum systems are used most commonly in the communication for anti-jamming principles. So the basic concept is that the information wave having small bandwidth is converted or spread by modulating it with over a larger bandwidth waveform. And specifically in the case of the global positioning system, the navigation message will have a bandwidth of 100 Hertz, whereas in P codes it is about 20 megahertz. This is a comparison. Next is the pseudo random noise codes. In short, we can call it as PRN sequences or PRN codes. So these codes or sequences are generated by using a tapped feedback shift registers having an appropriate hardwiring structure. So each CP or the clock pulse which is being given as an input acts as a shift to the bits to the right hand side. When we give a clock pulse for this shift, it will move towards right hand side. The bits will shift right side, where the content of the rightmost cell is read as output. And when we shift something, a new value will be present at the left side most cell. So that cell is determined by the binary sum of two defined cells, where a binary 0 is set. The bits in these two cells are equal. The choice of these defining cells is always arbitrary, and the property determines the choice of the defining cells is always arbitrary. That determines the property of the resulting code, where in order to make the procedure more clear, consider two or three cells which are defined. One after one clock pulse is initiated. The clock pulse is initiated, will be delivering a output as binary 0, and if you give 1, it will be sent to the next cell as 1 for the successive state. You can see a representation of that, the principle of tapped feedback shift register, where I have a sequence of 10110 in the table, 10110 in the table, and the successive state of this is that here it is being right shifted. So this one will come here, this 0 will come here, this one will come here, this one will come here. And this fifth bit in the initial state will be moving off. So we need to compare this and see what to put in the leftmost bit. So that will determine your pseudo noise codes. For this, we'll be using C bar A codes, which are generated by the combination of two 10-bit tapped feedback shift register, where the output of both the register are added again by binary operation to produce another set of code sequences. The codes of this registers are not classified. Why? Because this is being used as your civilian users, which is open to all civilians. A unique code is assigned to each satellite depending upon the defining cells, where the frequency of 1.023 megahertz and the repetition rate of 1 milliseconds results in a code length of 1023 chips. Hence, the time arrival between two chips would be just under 1 microsecond. Yeah, wait a minute. I'll start the presentation. Yeah, I will begin it from the. I'll start from the beginning. The course or acquisition codes that have been generated by the combination of these two 10-bit tapped feedback shift registers, having the output of both the registers, will be added by binary operation such that to produce a code sequence. These codes are not being classified since they are being used for civilian users. We had said about C bar A code since they are being used for civilian users, they are not being classified properly. Then we'll be getting a unique code, so which is assigned to each satellite depending upon the defining cells, the frequency of 1.023 megahertz, and the repetition rate of 1 milliseconds results in a code length of 1023 chips. Hence, the time interval between the two chips is just within 1 microsecond, which corresponds to 300-meter chip length, as I said earlier for CA codes in the beginning of this presentation. Next comes to the P codes. So the P codes are also not classified to a certain limit, and they are a combination of 2-bit sequences again generated by two registers. The first bit sequence repeats every 1.5 seconds, and the frequency of this will have a length of 1.5345 into 10 power 7 bits. The second sequence will have 37 more bits of this. The combination of the first bit sequence and the second bit sequence will result in a code with approximately 2.3547 into 10 power 14 bits that will have a lifetime span of approximately 266.4 days. Okay, 266.4 days. So the total code length would be partitioned into 37 unique 1-week segments. On each segment is assigned to a satellite defining its PRN number. We had said that PRN number 20, ID 20 will be used for 20th week and so on. Then these codes after completing are restarted at the beginning of every GPS week at Saturday to Sunday transition midnight. Okay, and we'll be having a chip code of 30 meters. This is your pseudo noise codes S1 and S2. For example, we take 010 for S1 and 10110 for S2. We'll be using a combination of 5 S1 with 3 S2. That will give us 15 chips. In a sense, 5 into S1 number of bits is 3. So 5 into 3 will get 15. Whereas if you take the next sequence S2 will be having what you call 1001 110, 5 bits. So 5 into 3, sorry, 3 into 5, we get 15. So by using this, we'll get a combination. So what we have to do is that we should repeat the first sequence I'll explain. In generation of the P code, 5 S1 is that is 0 1 0. Write it 5 times. 0 1 0, 0 1 0, 0 1 0, 0 1 0, 0 1 0. You get 15. And we have a next sequence considering 1 0 double 1 0. So write it 3 times. 1 0 double 1 0. 1 0 double 1 0, 1 0 double 1 0, and see that states are becoming, all the bit sequences of first bit and second bit becomes equal. And now use and binary operation. So most probably the binary operation that we use here is modulo 2 addition or XOR gate operation. So do modulo 2 addition of these two, 0 and 1. XOR gate operation output is 1. So we write 1. XOR gate operation 1. XOR gate operation 1. For 0 0 we get 0. For 1 1 we get 0. If any of the inputs is high in XOR gate, we get output as 1. So the combination will be getting like this. So the combination by doing the XOR operation of each bits, we get P code generation. So this is how to generate precision codes for two sequences. Okay. So next is the PRN code characteristics. So the PRN code characteristics of both CA code and P code is being given. So the chip rate for CA codes is 1.023 megahertz. So we get the chip rate of 1.023 in 10 power 6 bits per second. Chip length of approximately 300 meters. Repetition rate is for every milliseconds. Having 37 unique codes and easily to access. Whereas in precision codes or P codes, the chipping rate is 10.23 into 10 power 6 bits per second. Chip length of 30 meter and repeated for every 1 week, Saturday to Saturday, Sunday transition. Code type 37 1 week segment with having more accuracy. Okay. So this is about your satellite signal signature. Next topic is that we are going to see about navigation message. What does this navigation message consists of? How much time is required for transmission of your navigation message? What are its subframes? We'll see that. So the navigation message consists of the satellite health status, satellite's clock, satellite's orbit, and various correction data. Whatever the error being obtained, those correction should be done. So those data also will be present in a navigation message. So the navigation message will consist of 1500 bits divided into 5 subframes. So then each subframe will be having 300 bits each. Okay. So then each and every subframe will be transmitted for every 6 seconds, having 10 words with 30 bits. And the translation time needed for a word would be therefore, since it is 10 words in 6 seconds, for every word we require only 0.6 seconds for transmission. So each subframe will start with a telemetry word, which we can write it as TLM, having a synchronization pattern and some diagnostic messages. So these diagnostic messages are used for detecting errors. Each subframe will have a telemetry word, TLM. And the second word in each subframe is HOW, which is how. We call that how as handover word. This will identify the flags, the subframes. For that purpose, we will be using this handover word. And next is that we'll be having a word which consists of time of the week, which is TOW, tau, which counts the time and gives us the information of what time it is being given, which will give you information about the next subframe also. So sometimes this tau or the time of week is called as Z count and is always a multiple factor of 1.5 seconds. 1.5 seconds intervals since the beginning of the current GPS week. So if we start at Sunday, from that time onwards, whenever we want the time of the week, it will be 1.5 seconds interval of that. So this is your frame scheme of the navigation message. The total messages in a navigation will be 1500 over 30 seconds. Subframe will be having 5 subframes of 300 bits each, transmitting at 6 seconds, and words will be having 1 to 10 of 30 bits, transmission of 0.6 seconds. So the navigation message having subframes are being used for specific purposes. The first subframe consists of GPS week number, week 1, week 2, week 3, week 4, a prediction of the user range accuracy, users range in which position they are in, indicators of satellite health, like how much amount of power is left out, how much amount of battery, how much is the lifetime of that particular satellite or the device, so on. The age of the data, from which period to which period the data is being taken. Then estimation of the signal group delay, how much amount of signals can be delayed, and 3 coefficients for quadratic polynomial to model the satellite clock correction. In order to correct the satellites clock error correction, there will be 3 quadratic polynomials also in the first frame. The second and third frame transmits the broadcast ephemeris of the satellite, whereas the fourth and fifth subframe are changed in every message and have a repetition of 25. They will change depending upon the message being transmitted. So the total information thus will be in packet of 25 pages, requiring 12.5 minutes for transmission or 750 seconds as said earlier. And many of the pages of the fourth subframe, whatever we use in the fourth subframe, will be reserved for military usage. The remaining information or the remaining contents of information on the ionosphere can be used to contain the informations like UTC, Universal Time System, various flags, notifications, and the almanac data. That is your low accuracy orbital data information. And this is being considered for all the 24 satellites whichever is being present. The pages of the fifth subframe are mainly dedicated to almanac data and the health status of the first 24 satellites. Why? Because 24 satellites will be in orbital position, which will determine the accuracy of the position of the celestial body or the position of the orbit or position of the satellite which we want to determine. So the health status of that will be present always in the fifth subframe pages. And the pages of the fourth and fifth subframe will be always broadcasted by each satellite. Each satellite has to maintain this, thereby tracking only one satellite. We may get the almanac data of all other satellites in which they are obtained. So if you are able to find out the one satellite's almanac data, the remaining 24 satellites almanac data we can easily identify. Why? Because all the 24 satellites information will be shared equally in all the satellites. Thus the positioning, thus the information of CTC, various flags, information whichever is present in any one satellite, if you are able to take it, or if you are able to track that, we can easily track for the remaining 24 satellites which are being present in orbit, and we can come to a conclusion, or we can identify in which position the corresponding object we want to determine is present in. Okay, so this is about a navigation message.